Okay, we are at the next lecture on this computational Gabor analysis course. And I will start to do a unit now on 2D Gabor analysis. So I just wrote this morning some notes about general Gabor analysis over finite abelian groups. And evidently, the product of two abelian groups, like the ones that we have treated so far, two cyclic groups, is another cyclic group, as another finite abelian group. And we can do Fourier analysis. If we can do Fourier analysis, we mean we have something like pure frequencies. If we have pure frequencies and shift operators, then we can start to do Gabor analysis in an abstract way. And it's quite the same stuff, more or less, but you have to get used. And that's maybe one of the steps where a concrete abstract notation is getting quite useful compared to the multi-index processing that you would have. Just remember, if you're doing Fourier analysis, you have the discrete Fourier transform, you write sine and cosine, you find it's better to use the complex exponential function. Then you're doing double Fourier series, and then you have already multiple indices and summation issues and so on. Whereas if you say, well, there is something called a dual group, which is the collection of all the pure frequencies, and they form an orthonormal system, then it's quite easy, and you just have to understand what is the individual pure frequency. Now, just in words, everything is quite easy, and I will try to demonstrate it with respect to the applicability in Gabor analysis. Namely, plane waves are the pure frequencies for the two-dimensional setting. So what is an image? If you think of this in a signal processing manner, well, an image is a gray level matrix. Well, we would say it's a function of two variables discretized somehow. Now, what is the shift operator? And we have seen for functions which are living on a finite vector, it's better doing the cyclic shift. Of course, cyclic shifts are not natural if you just look at the image, which may arise as a segment from a larger scene, so to say. So cyclic shift would mean that you think that you pave your plane with tiles which look like the image that you have. And then, of course, you have sharp edges at the transition where you see the connection between left and right or upper and lower boundary or so. This, however, is a harmless trick because you can always window the signal at the end. So that's even what people do when they do Fourier analysis locally in the MP3 mode. They would represent, I don't know, 490 samples in the middle and zero padding at this boundary so that the FFT is not representing the sharp edge, but that it's representing the main content of the signal, which may be quite smooth and therefore well compressible. Okay, so you know I have this image C command, which helps me to display things and different things. It's more or less to show you that in this scene, you have different features with vertical stripes, oblique stripes, broad stripes, and so on. So we could also do here the same thing. So I'm trying to do this now in a direct way. The original would be the image scale of the signal that we have called double A. Maybe we do axis image so that it's the right format and show it once more. And so I think this is a good image, and okay, we don't have a color image here. So we do color map. That's not good. Map gray, and you can choose copper or other choices. And then you see this is the original image. So this is about 20 years old now. That's something that I took. And then I decided to just take a picture of myself. So this was taken maybe 1 hour ago. And essentially, I was storing this taking it over or by copying it from my mobile phone, and you see some features which are parallel stripes in different areas in different directions. So this is important because when I look at the Fourier transform of an image, I should know that it's not the FFT of the image. So MATLAB is not trained to say, oh, FFT for images is the right thing, because MATLAB thinks that a matrix is a collection of row vectors. That's why our command to create the matrix representing the Fourier transform is F equals FFT of I, or maybe FFT of I divided by square root of n to make it unitary. So there's a specific command that we have to do here, and that's the two-dimensional Fourier transform. Let's just see that, well, maybe we'll take this format and I'll show you that what the FFT2 is doing. So practically you can say it's doing the one-dimensional Fourier transform row-wise and column-wise. So I create now my Fourier matrix. Yeah, so FFTU is already the command. If I put a number, it gives me the unitary matrix or so. And now we know that, well, if this is a random vector, just to recall to you, of size n, we can either apply the matrix. It's a symmetric matrix. We don't have to take any transpose, or we do the FFT, which also preserves the format. And in this way, we see, first of all, that this is the right matrix. Well, there's a normalization going on, and this is with, well, multiplied with square root of n, which we have not done. This is because I took a unitary version or so. Okay, now what happens if I do this on an image? So we have now a random image of size n, complex valued, and then we can compare what happens if we do the two-dimensional Fourier transform of this random complex signal, or whether we multiply from the left and from the right with the Fourier transform. Now, that's the first comparison that I would like to make. And you see up to the normalization. So if I divide this by n, so this is kind of the square root of n squared is n, the factor which is wrong, you get exactly the same. Now, of course, we all know, and that's not surprising, that there are two possible interpretations of this triple product. I mean, MATLAB has no command for triple products. So you can either take the product of the first two matrices, they're all square matrices, or the second one. And if we do this, we see that we get the same result, but not identical result. So numerically it's the same, but as an outcome, it's different. It's a nice exercise. Maybe I do this as well. Yeah, maybe to show you, that's a kind of programming trick. Do a timer, or maybe, for example, first let me do a new section. I say maybe set is just our random vector as a column vector, and then I would want to show you for JJ from 1 to 1000. I'm not sure if this is reasonable. We do I just compute a XX with set, and then we finish and we stop how long it takes. Okay, so that's a harmless experiment, multiple frequency multiplication. And well, see, it takes some time. Not sure if it's running. Maybe I put it once more, yeah. And the other thing would be take f for JJ from 1 to 1000, do XX with XX with XX. And yeah, okay, while MATLAB is working, maybe I took a number which is too big. We will look how long it takes. So practically it means f with xx is Fourier transform is a command applied to a collection of column vectors. Now this of course means that you're doing column-wise Fourier transform. Then you have a new matrix and you apply it from the right. And from the right, it acts on the first row, the second row. So you're doing this row-wise afterwards. Here, you're taking the bracket first. You compute x with f, which is row-wise Fourier transform, and then you're applying it column-wise, and that's exactly what you should do. Okay. Now, while MATLAB hopefully is still continuing the work, or I'm not sure if there's any error, let me show you the Fourier transform of this stripe image. So we take this image, which has some plane wave features, as I would say. That's why I took this image. And you look at the Fourier transform. Now, if you look, oh yes, let's do the second one while I'm talking. Yeah, it's a good point to see. It's much, much, much faster. And you can say, well, that's why I'm doing a right matrix multiplication. It's much faster. Well, in reality, it's of course the question, the cost of a matrix multiplication, x with x, is n cubed. You need n squared scalar products, each cost you n multiplications, that's n third power. Here you have matrix vector multiplication, and therefore I would say let's copy this line here, because this was fast anyway. That's actually what I was thinking. And let's try to make brackets so that it's now a matrix vector multiplication, and that should work much better. So you see, sometimes it's good to be smarter than MATLAB, and you see it's a little bit slower, but it's kind of useful. You can speed up your code by a factor of, I don't know, 40 by just putting brackets in the right way. I must say that I even put comments to MATLAB that they should say automatically, you know how to do it, how to put brackets to have optimal or minimal number of multiplications. Okay, but what I wanted to explain is, for this stripe image, we can look at the Fourier transform. Again, the centered display is very important. And there is one other trick. If you would say, let's plot the Fourier transform directly, even the absolute value, because it's a complex valued function, you wouldn't see much. The information would be at the edges, so at the corners or so, and then you don't see it. Of course, what you should observe is that the mean value of a gray level image, assume it would be a random image, then you would have 700 squared pixels. And each of them has an average gray value, which may be between 0 and 256. So at least 100 is the average. So you would get a huge image, but with one information, which is just the average gray level at each pixel. So constant 1 integrated against this picture gives a huge value, whereas all the other things are the real information that should be put away. So what I'm doing is oh yeah, maybe that's even not what I meant. I think we should take the mean value. I will try it once more over the whole pixel image. And then we take the two-dimensional Fourier transform, so which means just one value in the middle is 0, but the rest is okay. And now you see some features. So this is the centered display. Maybe we put an axis. I have my plotx command to tell you where the middle is, plotx, and since this is maybe I put it in red. So what you see here is certain features, and it's important that the most prominent feature here is corresponding to the vertical feature. So this heater in the bathroom is shown prominently here. Now, if you look at this, what are you doing when you're doing Gabor analysis? You're looking at the feature of the signal at a given time window. And you're doing Fourier analysis decomposition into plane waves. So you try to go from a recording to the to the score. What we're doing here, we say we have locally different patterns, and these different patterns are representing plane waves. So we would think of taking a looking glass. I have no implementation for this, but we would go to a segment, and here I would say it's almost perfect with stripes which have this orientation. Now you go for the perpendicular direction, and you will see that this is this feature here. You see also there are some weaker informations here, and so on. Now, I have called the F striped 0. So this is the absolute value. That's the thing that we display here. The absolute value of the Fourier transform of this stripe image with 0 mean value. So this is what we see here. And then I determine the absolute value, maximal value, which is now reasonable, and look at the areas where this is larger than 1/100 of the maximum. So I'm taking those which are, or I will throw away those Fourier coefficients now for the whole stripe image, which are less than 1% of the maximal amplitude over the whole two-dimensional Fourier transform. This is, of course, again, a 0,1 function on the scalar domain, and I have this picture, and I have to tell you that this is slightly zoomed. So whereas this should go roughly from -360 to +360, you see only a quarter of the Fourier domain. Now what we do is the masked picture is we have the Fourier transform in the two-dimensional sense. We multiply it with 1 if the value is big enough, and we put it to 0. So you could say this is a hard thresholding operation with 1% of the maximal value. You can change it, and I was trying to do it at, if you do 1/1000, of course, this domain, the mask is bigger or so, but this is adaptive. And the idea is in Gabor analysis, you can do this adaptive thresholding, both with different thresholds at different levels, but of course also representing the local features very much. Now, if I do this reconstruction, and because it might have been real valued upon complex valued, I'm taking now the real part of this reconstructed function. I have to recall that it's a gray label image and reform it, and you see this is what you get. So we also see that yeah, maybe we could try to count the number of pixels. So what is sum of mask divided by n squared? So we have altogether, we have chosen, as you see here, 4,752 pure frequencies, which are plane wave coefficients. Of course, you have to know at which place they are taken. So for storage, it's a little bit more information than just 4,700 coefficients. But if you look at this, this is roughly speaking 1% of all the coefficients, and that's their representation. So of course you can imagine that when you do JPEG compression, you just have another orthonormal system with non-adaptive representation, so you would see something different, and that's how the thumbnails of an image collection are created. Now I have taken this other picture which was 720 by 720. And that's why I'm going back now to the two-dimensional Gabor analysis and really just do it from scratch. I must say that the general story would be that you choose some two-dimensional window, so to say, which could be viewed as a looking glass with soft boundaries that you move across your image. Then you choose a four-dimensional lattice. What we will do, we will choose a lattice we will choose two lattices, one for the first variables and one for the second variables. So roughly speaking, we have some Gabor analysis doing row-wise and some Gabor analysis column-wise. It's a bit less understood so far if you do a lattice in the time domain. So you could take a hexagonal lattice in the time domain and then choose the sampling of the Fourier transform in a hexagonal manner in the Fourier domain. I think that could be a good thing. But of course, you could also ask, can we have a nice optimal packing in the four-dimensional phase space, which has two time or location variables, x and y coordinates of your image, and two coordinates in the other direction. But there is much to do. So we do the very simple one, the so-called fully separable situation. And I've chosen to make it a bit more simple. The quadratic image, the one that we have seen at the beginning, and to say, well, what is a good choice of these Gabor systems? I choose Gauss system, and I choose A equal B. So for all the four different lattice constants are chosen to be equal. And I just take the largest divisor, which is less than the square root of n. So these are the, I think, nice lattice constants if you combine them like our 20 and 16 for n equal 480. So now we have 720. And so any pair of these two numbers is fine. I take the most, the least redundant one and the most symmetric one. So the redundancy, of course, can be computed, and I can do the dual Gabor atom. We can recompute it. We can get the redundancy of something like 20%, yeah, 25%. The dual window of this Gauss function, that's our Gauss function, has these features which you know already. It's the dipping at the center and the side lobes, because I mean the redundancy is quite good or close to one, not too close, but close enough. Now, just to remind you that we have a fast code or many different fast codes to compute the dual Gabor atoms, and also to reconfirm you, we can create the Gabor family with the same lattice constants, again, A equal B equal 24 in our case, from the window and the dual window, but it's the same as we would do by computing the pseudo-inverse of the whole system. So the pseudo-inverse of a Gabor system with the lattice is a dual Gabor system. Now, just for the dimensions, we have redundancy 1.25, so 5 over 4. And therefore, if you look what the number of Gabor elements is, it's 900. So the format, okay, so this is of course nonsense of both the Gabor system and the dual Gabor system is just 900. Now what I'm doing here is to transform it is just like playing domino. We would say that if you give me such a rectangular matrix and an image of format 720 by 720, the only way to multiply it would be to do this. Now you could say that you should do this by taking the row-wise action, which is the right expression, but then you could take the transpose of the corresponding, multiply it with the transpose of G and put it back to the original position. So that may be a way to understand that you're really just doing Gabor analysis. And of course, I'm sloppy or lazy, let's say, I'm just doing matrix multiplication. In the old days, I would have waited far too long, and it was important to use an STFT command and to put the information back into rows and columns. But it's also clear that what we get is a matrix of format 900 by 900 in this case. Now, how do you get back from these coefficients? And the answer is very easy. I mean, how do I get back if I have multiplied with, let's say, G prime? I have to multiply with the dual, with the GD. I do synthesis. And this is the same trick in a symmetric way. So just by what I call the domino principle, the dual matrices have to be used, that's clear. Put them in the right order so the GD prime fits to the G that we have put above to multiply from the left, and the G prime fits to the GD prime. Of course, we can switch the role as in one-dimensional Gabor analysis, of course, of using dual windows first if you're asked to have coefficients, and then this would be outer multiplication with G and G prime, which is just outer synthesis from Gabor atoms, row-wise and column-wise. And that would mean, of course, if you start with a one-dimensional Gauss function, you would have a two-dimensional Gauss function multiplied with the separation of pure frequencies. And these are exactly the two-dimensional Gabor atoms. Now, the same picture or a similar picture that we had for the stripe, and I don't discuss it now, for this first original image I had prepared earlier. If you zoom in, you also see there some horizontal vertical features which actually have a lot to do with the boundaries of the image, that the left and right are kind of significantly different. So usually you should ignore it and you should take a windowed versions with flat zero transition at the boundary, but you see also some vague entries which has to do with the stairs, with maybe the stripes, some periodicity, and the image gives you sampled or concentration along dots in this direction. We don't have to discuss it. What I think is much more important is to explain or to illustrate how these building blocks in the two-dimensional Gabor analysis look like. So recall that we have a system of 900 Gabor atoms. Our lattice constant is 24. Our signal is size 720. So we have to recall that at the first position, the first 30, 720 divided by 24 is 30. The first 30 building blocks are Gauss functions at the center with frequencies 0, 24, 48, and so on. And so if I take number 3, then the frequency would be 2 times 24, so it's 48 oscillations over the full length. And then, of course, it would be the row number 49 of the Fourier matrix, because we start with 0 oscillations being in the first row or column of the Fourier matrix. 5, of course, is 4 times 24, and that's 96. And so we would have a plane wave where in one direction you have 48, profile of 48, and in the other direction of 96. And if you localize it with a two-dimensional Gauss function, recall that we are zooming in very much like it's a factor of 10 instead of minus 360, so factor of 5. Minus 360 to 360, we see something like this. Now, if I change, and that's just for illustration, from some small in the vertical direction, so I'm taking this in the vertical direction, so it's a product of a n times 1 matrix with a 1 times n matrix giving me a table of multiplication. It's this building block, and it's a complex valued function, therefore I have to show the real value. Now, just to illustrate what happens if I don't do the gray label image, and I also change here from 4 and 2. That was an old notation. Then you see something like this. And this should convince you that there is no difference from the same object. We take the real part or the imaginary part. Well, it's like, do you hear whether you have played a sinusoidal tone or a cosine tone? While all the shifted versions are always having the same frequency, giving the same musical impression. Here is some effect where you see how does it change with the frequency. And of course, 28 is very close to the highest possible number, which is 30. You have to think that we start with 0. So 1 is, or in the Gabor system, at level 2, that's the closest. 29 would be the same. Maybe we change it. Maybe we change it to 3 to show you the symmetry. 3 is 2 to the right of 1. 30 is minus 1. So actually we should take maybe 4. So 4 is 3 away from 0. So 4 is 3 away from 0. Whereas 21 is minus 1 is 30, minus 2 is 29. So let's see what we can get here. So the point is that these are just the same frequency in terms of how far away you are from 0. So one can say that the description of, yeah, oh my God, the same axis in yellow. So the frequencies are described by the amount of oscillation and the orientation. And the frequency domain for such objects, you will see a peak. The peak is further away from 0 if the oscillation is high. So you would say it's a high level ripple pattern that you have here. And the orientation is by a normal vector. So this is the connection between where in the plane wave picture or in the Fourier transform two-dimensional Fourier picture do you see the contribution. Okay, so what are we doing when we're doing this two-dimensional Gabor analysis? We're essentially decomposing a picture into this. And there is the same amount and problem of redundancy that we can do this in many different ways. So finding the dual windows, and of course you have to prove that the dual window of a separable situation is just the tensor product of the dual windows. This is what we have been doing here in the reconstruction business, that we have really can compute with this process the best possible, the cheapest representation. So the minimal norm in the sense of this scheme of coefficients, which is sitting on a 4-dimensional lattice, but we don't have to worry about this. This is theoretically justified. Now the transform, that's the next issue I would like to discuss. The transform of this is a matrix of format 900 by 900. But here you see, if you look at it, you have some concentration. And now the question is, well, how can we visualize a function on a 4-dimensional lattice? Well, we have to reorganize it. And in the way how we have been doing it, we have fixed the lattice and then we went through the frequency blockwise or so. So what you could say here, if you zoom in, we have already done this very strongly and it's very localized or so, is that the information that you have at these places is, this is the spectral information that you have at a given point in the image. So if I would read out that this is something near the center of the image, then the contribution would show, is there much of, is it dark here or is it light dark? Is it oriented in some direction or so? So this is the information that you have. Now, the master thesis, which was doing this, so the first one who was doing such experiments was Peter Prinz, who wrote some code also for Gabor analysis. But then Stefan Paukner was doing a nice master thesis, which is also absorbed in an article in the Handbook of Image Processing. And so he said, well, or we discussed it, and we should also be able to sort in a different way. So instead of time frequency shift, you should have a frequency time shift. So you should sort by frequencies. So you should say, first come 0 frequency at all the locations of the lattice. Then you do the next frequency. So you make a numbering, a numberation of the frequencies, the plane waves in a particular order, namely the MATLAB order. And then you go from position to position. So this is just a transformation, the kind of index transformation, which makes out of our standard way the new one. And then I'm doing just the same trick as before. I'm multiplying with this GTF, and I get an image of the same format. And if I look at this, it looks very similar, just because it's very concentrated. I mean, our image. But now I think, if I remember correctly, this is concentrated though. So this tells you there is not a spectrogram at a given image, but the representation of the image, or now you fix the wave number. So you're asking, where in the image do I have a lot of horizontal stripes of a certain orientation? And then you would describe it in such a way. So this is just a different way to organize this data. But if you're taking the question of thresholding, and if you have a uniform threshold, we have a fixed routine, and this is the routine which is called, oh, it's not here. Something has been left out. Yeah, so I'm not sure if I find it here. No, that's surprise. Yeah, okay, it's dem gap. Help dem gap 2. Yeah, so this is a way to, not sure where, maybe I didn't insert it here, but we can hopefully run it quickly once more. So our image is called AA. And so this is essentially doing what I was doing by hand. It determines a filter, it outputs one-dimensional and so on. And now we are trying to take a look at the filtered version. So image C of a filtered color map gray. And I don't want to investigate now the values here, or axis image show. Yeah. Okay, so we should open a new figure. And you see that we have more or less the same effect that I was showing you with the stripe image. But whereas it's kind of, you see the adaptivity or so. And you could also decide that I want to show only the biggest coefficients. So in this case, you see very clearly, here are vertical stripes, but here are also fine stripes in different directions. Here, this is a little bit eliminated, but whereas if you would choose a threshold uniformly over the image of the Fourier transform, these fine details would be completely destroyed or so. So this is actually kind of a good way to demonstrate what is going on. And I think that's more or less all I have prepared for today for this two-dimensional Gabor. And so I will finish the recording now, and thank you for your attention on this here.